Today's workshop will be about computer vision application and why we choose to deliver workshop about computer vision. Current lockdown kind of push people from other fields to help doctors and others who fight against coronavirus somehow, and we decided to make our kind of attempt and share to help them somehow. And this workshop will be about to build a computer vision application, which we will be able to detect if a person wears face mask or not. And this will happen in real time. I mean, in real video stream. So that's kind of all about us. And let's proceed with the small outline of this workshop. Here is it. And there, as you see, there are some parts of this workshop. In the first part, we briefly talk about convolutional neural networks, how they work and how it helps us to deliver our best results in computer vision tasks. And after that, we will talk about how we generate and collect data, and then model architecture, which neural networks we chose and why we chose that particular model architecture, and how we build and train the model. And after that, as natural, comes the performance evaluation of the model, how it generalizes on the outside the training data. And at the very last part of our workshop, we will have some coding, and where we will see how our application is deployed on real-time videos and how it performs and how it detects if the person wears a face mask or not.
Sorry, Nodar, I put the link of the GitHub repository, so you can git clone the project.
Oh, thanks. So here is the, and I can provide you all with the link. How can I get this?
I put it in the chat.
Okay, thanks. And you can clone this repo and you can follow me with this structure. It's very simple one. So let's continue. Oh, sorry, there is this. And let's briefly talk about what are the convolutional neural networks and how they work. When we have some computer vision tasks, either it be in classification, when we try to classify some objects on the images, it can be a cat or dog, or classification and localization tasks where we try to classify objects and then localize this object on the image, or kind of object detection, which objects reside on the image, or instance segmentation. All the time we use convolution operation. And this convolution operation helps to achieve our kind of the final aim. What is this convolution operation and which parts consist of it? One of the most important parts of the convolution operation is the kernel, or also known as the filter. This kernel is a small matrix, and this small matrix is used to manipulate on the picture. Okay, the computer sees the pictures. Computer cannot see the pictures as we see, and the picture for computer is just the matrix of numbers, and this small matrix kernel is used to manipulate this picture somehow. And I think that we at some point of time we all use photoshopping, and this at the higher level of abstraction, it's kind of same using photoshopping, but with the numbers and codes. For example, if you follow these links, you will see some well-known kernels. And for example, if we want to have some blurry pictures, we need a different kind of kernel. If we want to sharpen the edges on the objects of this image, we need different kind of kernels, and so on and so on. Convolution operation has its dimension, and actually this dimension depends on the dimension of the data. Here we see that this is at the leftmost part, we have our input. The dimension of this input is 1, so we have one-dimensional data, and henceforth we have in the middle is kernel, one-dimensional kernel, and this is some random numbers here for some expositional purposes, and to see how the convolution operation works in practice. So at the rightmost side we have output, and applying kernel and convolution operation is just applying this kernel to this input. So if we apply this kernel to this input, it's just we take element-wise product, and after that we sum them these elements, and we get the output. Also note that after the convolution operation, how the size of the output kind of shrinks. It means that after the convolution operation, we lose some information, and that's totally acceptable. But if still want to maintain the size of output to be same as the size of input, we can introduce the new notion, new concept of padding, which means to add trailing zeros at the left and at the right side. And also note that we used step size 1 when we apply this kernel to this input. And what happens if we allow our kernel to slide with the step size 2? I mean, here we take this 1 times 2 and 3 times 0, 3 times 1. And what happens if we slide two steps at a time and we take this setup? 3 times 2 and 0 times 1 and 1 times 1. Here is the example, and we introduce here with those new notions, as I told you, padding and stride. Padding is this number shows how many zeros we add at the left and right side, and stride is the step size, or kind of you know how the sliding window works, and this is the same. This number shows how many steps our kernel will take to evaluate the output. So here, our kernel starts from here to here and ends here, and the next second step starts from this 3. The third step starts from 0, and so on. Sorry. This is one-dimensional convolution operation, but this convolution operation is very, very suitable for the one-dimensional data. And this one-dimensional data has one common special dimension, which is the time, and henceforth this data is called also sequential data. Sequential data is time series data, and some text is especially in natural language processing. But one-dimensional convolution does not work for images. You know, images have 2 special dimensions, which is the height and width, and for that reason, we need to have some other, some higher dimensional convolution operations. Do you have any questions up to now? Okay, now we can. Am I too fast? Okay, we can continue. Here is the 2-dimensional convolution, and okay, take a look just as that the 2-dimensional convolution is to filter the image somehow. Use some kernel to filter the input image. Here is the Geoffrey Hinton's picture, and this is our kernel, and this kernel helps us to detect edges of the picture. So this is the output. We apply this kernel to this input, and we will get this output. And here we see that the edges are more sharpened than in original input. And also note that in 2-dimensional convolution operation, we slide our kernel in 2 directions. First is left or right, and second is up or down. Okay. And here, this is kind of the continuation of the previous slides, and the logic and intuition are the same. So we have here some random matrix and some random kernel and the output. And this input is for grayscale images. Okay, grayscale images have widths and heights and the depth of these images is 1. Henceforth, we have this one matrix. But if we have colored RGB channel images, these colored images have 3 channels, and we will have, or we would have, three matrix, this kind of 3 matrix stuck on each other. And I will show you how the convolution operation works for colored images. But to make it simple, let's review this example. Here, applying convolution is the same. We take element-wise product and we add them up, and we get this output. But to recall the padding operation and stride, here is it. If we want our output to be the same size as the input, we fill with trailing zeros, and we see that the output is 4x4 matrix as input was. And what happens if we move our kernel with 2 steps at a time? And this is the stride of step size 2. And stride allows to slide our kernel. And this is the first step. After first step, our kernel starts with this small matrix, then this matrix, and then this. And we will have this output. But there is some alternative of stride. If stride is more than 1, we can use different kind of technique to effectively reduce the dimension of the output. Okay, so applying the stride more than 1 means that we effectively reduce the output size. Okay, from here from 5 to 5 to 2x2 matrix we got. So the alternative is to use some type of pooling, and in this particular slide we are reviewing in one subtype of pooling, which is a maximum pooling. So this is our input matrix or input image, and here we have some, it does not matter, some kernel, and what matter is the max pooling. How it works? It applies our kernel and picks up only the maximum number from here, which is 9 in this case. Here is the 7, and here is 8, and then 6. And we will have this output, which has lower dimensions, I mean height and width. And I think, so now we can see how the convolution works for grayscale images. I have some GIF here, and as you see, this is the input image, which is a grayscale image, and this sliding window is our kernel, and we see how the output is generated. How
here is an image without a padding and stride equals as we see.
Oh, thanks also. I almost forgot to mention that. Yes, just this is a padding 1 and stride 1. So it starts from here and follows with the step size 1. And how it is. So this was the 4 grayscale images, and let's see how it works for 3 channel images, which is a colored image. And here it is. For colored images, we have 3 channels: red, green, and blue. That's how the colored images are built, and this kernel works and produces this output. And actually, this is how the convolution operation works. Okay, and here, as Soso mentioned, this padding is, it's not shows up here, but let's say that padding is 1 and stride is 1. Okay, so now we can consider how the convolution operation works for the whole model. How the model building starts and ends, and what is this architecture. So, but for this we need to define why we need a convolution operation and what its role in this convolutional neural networks. So we use convolution operation to extract features from the images. Okay, let's imagine we have 3-layer convolutional neural network. At the first layer, the convolution operation tries to extract the most simple features from the images, such as the vertical lines and edges or horizontal lines. Okay, these are very low-level features, just lines and some edges. And in the second layer, the output of this first layer is the input for the second layer, and in the second convolution layer, the convolution operation tries to build some mid-level features, and these mid-level features can be eyes, nose, and ears, depending on the image type. And after that, the last layer in our imaginary network knows how this, so for the last layer, the input is the output of the second layer, and the last layer already knows where is the nose, eyes, or ears, and where are the edges, and then this last layer constructs facial structure. Okay, so at the high level, the intuition is and key insight is here that each layer of convolution is necessary to extract features, and at each level or at each layer, we increase kernel, the amount of kernel or the number of kernels to extract more and more important features. Okay, imagine here the number of kernels, say it's 32, and after that we can have 128 or 512. It depends on your aim and project or task. So let's generalize this setup. And if we have, what happens if we have more and more convolutional layers? So this picture shows exactly that, what I told you. Here at the start, we have the image. It's a cat. It's the colored image, and here are the three channels. This is the first convolutional layer. And here the channels is the number of kernels. How many kernels we have in this convolutional layer, and it can be, as I told you, 64 or 128. And then after that we have second convolutional layer, and at the output of this layer is the input for this layer, and okay, say that the first convolution layer extracts these low-level features, then this second layer extracts these mid-level features. After that, with these dash lines, we can consider here some activation functions, or we can apply max pooling or stride. It depends. So this third layer extracts, say, these high-level features, and they already know where the face is located or the object is located generally on the image. And then here also can be, again, the max pooling or average pooling. And at the last part happens the flattening of these matrices. These, all the input and output of this convolution layer are matrices. And the sizes or dimensions of these matrices depends on the number of kernel and also the dimensions of the original input. This is particular case of RGB or colored image, and here and this is for the grayscale image. How the whole model works for grayscale images. Okay, this image comes from the MNIST dataset. It's well known, and everyone, I think everyone in computer vision starts with playing with this dataset. And here, this is our first convolution layer. Then comes the max pooling. Here can be, in between can be some activation functions. Then the second convolution layer. Then again the max pooling, and yes, at the last part here the flattening. And these green dots and these edges are the common neural network which is responsible for classification. Okay, with MNIST data set, we classify numbers from 0 to 9, and this is here we see. And here also this is some common neural network, and this neural network is responsible to classify objects on the images. In this particular case, we have cat, dog, or car, but this is for picture for cat. So now we can proceed as we have some general understandings of how the convolution operation works and how it helps us to achieve our aim in computer vision tasks. We can now proceed with how we collected data and how we pre-processed and generated it. In this part.
Sorry, Nodar, maybe someone has any questions. So if someone has a question,
okay,
open.
Any questions so far? Is it everything clear? I can repeat as many times as necessary, okay? No? Good. So, before we deep dive into data generation process and how we collected it, it's necessary to clearly define, or it's good practice, say this, to clearly define the aim and what task at hand we have and how we approach this task. So for this task, for our workshop, we have kind of the classification and localization task. First, we try to detect faces on the image or on the video, and then we localize those images, and then we conduct classification to find if the person or human wears the mask or not. Giving this, as also considering that the images for faces with a mask is somewhat scarce, we decided to use data which was generated somewhat artificially, and how this data was generated. This process consists of the two steps. The first step is here to collect normal faces without masks, the images, I mean, and after that we can apply some computer vision trick to apply face mask to those faces. So, and what is this trick? This trick is here to use facial landmark, which automatically detects facial structures such as mouth, nose, and eyes, and then applies mask. And to understand this process more clearly, we can consider this example. Okay, this is our starting point. We have this image, and then we try to detect the face on this image, and then after detection, we apply facial landmark technique, and we localize and we find out where the nose and mouth is located. After that, we have the picture of mask, and we apply those masks to this face. Applying face detection gives us ability to compute face bounding box. This bounding box is the coordinates of the face or the numbers which indicates where the face is located on the image. So as you see, this gives this red box. And after this, or having the bounding box of the faces, we can use facial landmarks and localize facial structure. So this red crosses indicates or gives us the exact coordinates of the nose and mouth, and this. And now we can apply the mask of this face. So applying mask, and this is the last step. Applying masks gives this image, and I know that this is not the perfect image to have, but this was enough for model training and to generalize well. So, but also note that using this technique, I mean this data generation process has one drawback, which is that we cannot reuse this image for training process, as the image indicating person which does not wear the mask. Okay, because if we do so, this will cause to degrade our model's performance. We will introduce some artificial bias, and our model will not generalize well on the outside the training data. Okay. So here is this, and I think now, as we have an understanding of how the data is generated, so we can proceed with the model architecture and talk about which model we choose and why we chose this model and how this model is built. Anyway, but before that, I cannot see. Is there any questions? Should I see here? No, I think no.
I think questions we'll go through questions at the end. People will write them down in chat or Slack group, and then we can read them.
Oh, that's much better. Okay, that's much better. Thank you. So, model architecture. For our workshop, we used model architectures which are mobile nets, and these mobile nets are highly efficient and optimized for embedded vision applications. And there are two main types of mobile nets, which are mobile net version 1 and mobile net version 2. And let me explain these two models in details. And so, in contrast to standard convolution operation, those models use depth-wise separable convolution. And I will explain in detail in a moment what is depth-wise separable convolution. So we see the general architecture, and I will refer those models as V1 and V2. Okay. So let's start with V1. Mobile net, as I told you, mobile nets use a depth-wise convolution operation, separable convolution, and this kind of convolution operation gives us the possibility to dramatically reduce model size and complexity. Now, what is the model size and the model complexity? Smaller model size means fewer number of parameters. We know that the generally neural network sends millions of parameters at each layer. And here, smaller size means fewer model parameters, and the smaller model complexity means a smaller number of operations conducted at each layer. And this smaller number of operations is multiplication and addition. Okay, now what is this convolution operation considering all of this makes these models very suitable for mobile phones or devices which has limited computational resources. Mobile devices or Raspberry Pi or NVIDIA Jetson Nano, or we can consider Google's Corel. And also, so what is depth-wise separable convolution? To understand this concept, I will break down this into two parts. First is depth-wise convolution, and this is standard convolution operation, what I was talking about in previous slides. And this convolution operation is applied on each channel. Okay, imagine we have one colored image, and this colored image has 3 channels, RGB, and this kind of convolution operation is applied on each channel separately, and the outputs are stacked on each other. After that operation comes pointwise convolution operation, and this pointwise convolution operation is just one-dimensional convolution operation. And the combination of these two types of convolution gives us depth-wise separable convolution. So, and what is the difference between those two versions of this mobile nets? V2 version, in contrast to V1 version, has 2 blocks, as we see, and it also uses depth-wise separable convolution operation, but the last layer of this network is linear layer. And why we choose, or why the creators of this network chose to have linear layers. At this point, this is the convolution operation. Here is the depth-wise convolution operation with activation of ReLU. And the last layer is a linear layer. There are experimental evidences that at this layer we have small information. And if we use non-linear layers such as the ReLU, we lose even too much information. Then that will causes our model performance to degrade, and it will not be able to kind of perform classification or object detection tasks. As this network is highly optimized for limited computational resources, we prefer to use this, as our application can be deployed on the mobile phones and use it for live stream videos. And why this version 2 is much better than version 1? Compared to version 1, version 2 is much faster and uses 2 times fewer operations. Fewer operations, I mean multiplication and addition, and have 30% less parameters. Here are the on the slide there's the text what I was talking about here, and let me skip this. And here there's on this table there's a comparison of MobileNet v1 and MobileNet v2 on the ImageNet dataset, and these two architectures performed image classification tasks, and we see that version 1 has almost 600 million operations. It needs 600 million operations, while version 2 needs 2 times less, almost 2 times less. And this column shows the number of parameters, okay, in millions. 4.2 million parameters for V1 and 3.4 million parameters for V2. And this first column shows the accuracy. And taking into account the smaller size of version 2, accuracy is higher for version 2 than in contrast to version 1. And that's why using MobileNet version 2 is preferred in this case. Is it clear, everything here? And now, as I defined the architecture of the model, and we know how the convolution operation works, and also we know how data is generated, now it's time to build and train the model. I pasted some important parts from our code, and after this presentation we can review the code step by step, and you will be able to follow me and to train the model if you want. Or also we have trained model, and you can use this trained model to perform a face mask detection in real time. So, but before model training, we use the data augmentation technique to have a new training data, where we introduce some random rotation, zooming and shifting and flipping the images. And here is our base model. And base model is defined as MobileNet version 2, and we use the weights of pre-trained ImageNet. And as I told you in the previous slides, here I think this should be this one. The first few layers of convolution operation tries to extract most simple low-level features, and taking into consideration this was the reason why we used the pre-trained ImageNet weights, because it's much better to use weights coming from this huge data set than you start your training process from scratch and will not achieve desired results. Also, we excluded the head layer of this network because we want to have our head layer. So the output of this layer will be our model's input. This is our base model, and in the next slide, we will define our head layer. Okay, and this is how our head layer is defined. Our head layer is the output of the base model, and base model is this one. Okay, and we introduce some layers, some extra layers. This is the average pooling layer. After this average pooling, we flatten the output of average pooling layer. After that, this flattened the output of this flattened layer will be the input for the dense layer with activation review. And after that, we drop some neurons with the probability of 0.5. And this is kind of the norm regularization technique for our model, not to overfit. And after that, after the dropout layer, we have dense layer, and we use activation of softmask to perform classification tasks. Okay, we have two classes: either person wears the mask or the person does not wear the mask. And here, this last line is our model, and it's ready to be trained. And also note that for optimization, we introduced Adam as one of the strongest and well adopted optimizer function in this kind of task. And here comes to model compilation. This is very specific for TensorFlow and Keras. And for this workshop, we used TensorFlow and Keras to train the model. But you can give a try and use PyTorch or some fast AI. And if we did not compile the model, it will throw some errors. And this is actual training. This last part, we fit the model, we use our data here. And for epoch, we used 20. Actually, we use 20 epochs to train the model, and that was all the way enough. And so, as we have classification tasks, we can use some common classification metrics to assess model performance and to see if our model overfitted or underfitted or just performed what was expected. For that, here you see some classification reports, and our model achieved approximately 99% accuracy. And here is also this graph shows the model training and accuracy. And as long as those two lines follow at each other and does not diverge, we can see that our model does not overfit. It's just good. So I think this is the very end of our presentation, and we now review the code and perform the live demo of our. But before doing that, I want to give you some additional resources, and these are some resources which explain even in depth of how this model architecture is built. And by the way, this model comes from Google. And this is the very end of this presentation. Any questions, or we can continue with the coding part? Okay. And for the coding part, let me this is our workshop structure or kind of project structure, where we have three main files or scripts, and we used this code for model training. And I will briefly overview what was the parts of this code. Here we have some general and common imports. And as I told you, we use TensorFlow and Keras. This function is used for argument passing, and you can run those scripts in terminal, and this function is used for to pass the arguments typed in terminal. And here this loop is responsible for to find where the images is located and parse them. And here we create a numpy array of labels. Labels are 1 and 0, 1 means that person wears face mask, and 0 means that a person does not wear the mask. After that, we perform binarization of those labels, and we split our data into two, training and testing. We use 80% of our data for training purposes and 20% for validation of testing purposes. And this is image generator. As I told you, we use data augmentation technique to have new training data. We randomly rotate, shear, and flip the images. And this is the base model, but this base model does not have a head layer, as we want to have our new head layer. And this code is responsible to create our new head layer. And the input for our head layer is the output of the base model. Okay. Then, this also note that this code freezes some layers in the base model. And after that happens here the model training, and we also serialize our model for this line of code is responsible to serialize our trained model. Serialization means to save the trained model on the disk. Okay, and you see here, this is the saved model, and these lines of code are responsible for this graph. Okay. And after the training process, we saved our model on the disk, and we can now perform how it performs on the training set. And for this, we have this script is responsible to test our model on the static images. And here's the same, this imports, and here is the argument parser function, this one. And then we read the images, some testing images, and we create image blobs, and this is the input for our model. And then we put our image into our model. And here, with this for loop, happens the prediction process. First, on the image, our model tries to detect face. And after the face is detected, we perform mask detection on that face. And that's all. And now we can continue with the demo to see how our model performs in real videos. And for that reason, I have the notebook here. Okay, and I can run this notebook and see what will be the output. Okay, this is some command to make sure that we are on the correct path. I mean, we have all the necessary files. This is our serialized model. And we will import some, okay, we use OpenCV to switch on our camera and perform live streaming. And this function is responsible for detecting face, and on the face detect if face has mask or not. For that reason, we also know that we have some threshold parameter here, and I will tell you soon what is this threshold. But this first frame parameter is each frame coming from our live stream video. Okay, video consists of many images which moves very fast, and this algorithm, this parameter is responsible to detect face, and this parameter is responsible to detect if face has mask or not. Here, with this loop, we set some confidence, and this threshold parameter is okay. Our at the last layer, our model returns probabilities, and these probabilities shows if face has mask or not. Okay, if probability is high, we are more certain that the face has mask, and if lower, face doesn't have mask. And also, we define this confidence, and if our confidence or model's predicted probability is lower than this threshold, we say that this face does not wear the mask. And one of the most important line of code here is this if condition. If our model did not could not detect face on the image, hence the prediction will be has mask or not. And this function returns the location of real face and prediction. So this is just function. We can run it using Shift Enter. Works for me. Maybe in some cases Control Enter work here. And with these lines of code, we read our model, which we serialized here or saved on the disk. And we use some pre-trained weights from ImageNet for face detection. And this is our model to detect if face has a mask or not. Let me run this, and I think my camera is turned off, and this will work. And this is the last part. This line of code turns on my camera, and you will see my face. And this while loop is responsible to read each frame with this live stream, then resize this frame to match this the sizes of window, and then happens the prediction. And if we press the Q on our keyboard, this application will stop, and there's some cleaning up. Okay, let's see how this works. The camera is turned on, I think. Yes, and you will see me here. I'm not wearing the mask. Okay, and it detected face. As I told you, now let me take my mask, and here, and if it, yes, it works. Yes, yeah, you'll see how it works.
Now that it may don't work on a black mask, because in the training set we have only white masks.
Yeah.
As I found out a couple hours before, there is also new datasets of much wider masks, so you can train this model on the dataset. So.
Okay, so we'll see how it works, but let me check if it works. This is a blue part, and it still says that it's white. Okay, and I think for the black mask it just doesn't work because it don't know how to differentiate and discriminate black or other colors of masks. So I will turn off this video, and if it takes some time. So I think this is the end of our workshop. If you have some questions with the codes, we can answer these questions, or you can run this training and fine-tune some parameters to have even better model than we have, or anything else. Is everything clear, or we can go back to slides?
Nice. Also told that it works on a black mask.
Oh, sorry, I did not.
It's wrote in the chat. We included in tutorials. This code is part of the tutorials, so we include links, and if something is not clear, you can read those. So they are on ask us before. And there is also a tutorial how to build the same on a PyTorch. It's a framework of deep learning as a flow.
Okay.
As far as we know, on the dataton, you have to build something like that. So if you have a question, ask us. No problems.
And also, I want to add some. Here you see. Oh, This is great source for learning, and also this will help you for datathon to build something cool. And there you will find some notebooks and real world, real life examples how you use convolutions, especially these notebooks. And this is School of AI, and our company Maxim AI conducts these lectures every week, and also make notes that from the next year we will start our new school, and you will have chance to apply for that school. It's totally free, and there are amazing lecturers and amazing people deliver those lessons, and also most importantly, those lessons are suitable for real world, and it's just not textbooks. Okay. So now can I stop sharing the screen, or are there some questions? I think it's a little bit early to finish, but we were expecting questions.
So if anyone has any kind of question, it is the best time to ask now. Thank you, Nodar and Josep, for your presentation. It was very nice, and thank you for your time and for your effort. If anyone has question, you can write it on Zoom chat or Slack group or raise hand. But as we can see, no.
Okay. Thank you, Irakli. Thank you all for listening to me, and and that was great experience delivering this workshop. Thank you.
Let's go to our last session for today, and tomorrow we have datathon, which will be fun, very interesting, and many surprises are waiting for people there. So do not hesitate to join. Thank you.